So okay, welcome back. So we're going to finish off the business with some more algorithmic considerations. Yeah. So remember from this morning, the last thing we did was reformulating the filtering and smoothing problem as sort of a augmentation of the given stochastic or the underlying model. And that's very much in line with what the ensemble Kalman filter does. I will, for a little while, continue doing it in the time continuous setting because it's just a nicer formulation. And then I will switch to the time discrete context and then discuss a few specific things about the ensemble Kalman filter and how it links into other type of filters. So, and again, I think the innovation that came through the ensemble Kalman filter of thinking this way is really a tremendous achievement because it really changed the perspective how people look at the filtering and data assimilation perspective. Anyway, so here again is the linear setting, and in this formulation where I really don't look at the mean and the covariance anymore, but I work directly with the process. And now you can right away apply Monte Carlo. You can say, I sample from my initial distribution, and then I produce realization of the process, solving the SDE or the differential equation model, and then I get this additional term, and for that additional term, all these particles have to talk to each other because you have to compute the mean and the empirical covariance matrix. And that's why it's called an interacting particle system you get. So it's just through the data it speaks to each other, because otherwise the models, as you know, the forecasts, you can run them entirely independent of each other. They don't see each other. So it's a standard stochastic process. So it's a different type of process which actually plays a role. These kind of processes play now a role in lots of fields, like if you go game theory, and so, because then also if you think of each particle being an agent in a game interacting in some way or another, then you get the same kind or similar structured problems that leads to these players or agents interacting with each other. So this is a particular game we're playing here, and all agents cooperate in a way. I mean, actually, if you want to put this a little bit further, you can say if the system is chaotic, actually each agent tries to get, in a way, do different things than all the other agents. So that's something that tries to repel each other in a way and explore all the possibilities, but then they cooperate through the data assimilation where they sort of pull each other together again. And that balance of the two is basically the game the data assimilation plays, or the ensemble Kalman filter. And if you would use different interactions or different things, then you could play, if you go away from data assimilation, you could play different kind of games, and you just use different kind of cost functions or so, and then you get different interactions. But still the philosophy behind would remain sort of similar. So I once gave a talk actually entitled Playing Games with Data. Anyway, so that's down here. That's what the ensemble Kalman filter does, or would do in the simple setting of a linear system. And of course, if you asymptotically, it will be entirely correct if you draw enough samples. Of course, in the linear case, there's little reason to do this. There are better ways of doing it. Now, if you go to the nonlinear case, as I said, there's this feedback particle formulation, and the augmentation, the innovation looks a little bit different. Again, there are actually two ways of, I just wrote down one, but there's another one with perturbed observations. So you add a stochastic perturbation to what your model says the observation should be, and you compare it to the actual measured stuff. And that's the innovation, like in the stochastically perturbed ENCAV. Or you have this version, which is the square root version of it in the time continuous limit. And then again, if you play you do the approximation of the Kalman filter, this is a constant matrix. Now you can also play this backward, this game, and say if I want to have the smooth solution over the whole interval, I have to integrate backward the equations. Now this sounds like a bit like a horrendous thing to do, in a way it is, because normally if you integrate your model dynamics backward in time, you have diffusion, stuff like this, so that's unstable. You're solving an unstable, backward in time unstable system numerically. That's not a good thing to do. But what stabilizes you is this term, essentially, that augmentation that always pulls you sort of back, and it just gives you the right combination. And again, you can then do this, put this into a Monte Carlo context, and so you would have a smoother Monte Carlo approach to this. So that's what's where we go. So we had this. Yeah, so this would be the Ensemble Kalman smoother. Of course, there are other ways to compute the smoother as well. We heard Greg talked about this yesterday, where you're actually not solving the model anymore. You're just computing correlations between a certain time and past times and future times. That's another way of getting the smoother solution, which is actually quite robust, but it can, of course, lead to trajectories that don't really match the dynamics. So there are pros and cons for these approaches. Okay, so let's get to the discrete time case now, because that's, I guess, what most of you do in practice, where you have observations at discrete times, and then you basically talking about the forecast and the analysis. So the forecast is what the model predicted, and then you try to adjust the forecast so that it in some way reproduces the posterior distribution once you've seen the data. And so this is the notation I'm going to use now, is the forecast. This is in the previous notation, that's given all the data to n-1, and that's the forecast at Tn. That's the forecast. That's now the forecast, the solution at Tn. And then the analysis is basically just switching the second index here, incrementing it by 1 because you take the data into account. And the observation model, it can be nonlinear, but it can also be, I will put it down as linear here for simplicity. And there are various ways of thinking about the Ensemble Kalman filter, but the one way is that you extract from your forecast, you extract the first two moments, the mean and the covariance matrix. And then you do the standard Kalman update formulas. Assuming also that your likelihood is Gaussian, so the measurement error is Gaussian distributed. So you have a Gaussian approximation to your prior. The likelihood is, let's say, already Gaussian. And then the product of two Gaussian is Gaussian again, and it leads you to the Kalman formulas. And so the posterior is Gaussian. And so you get the mean and the covariance out of this approximation. And then the trick again is to convert this into something that actually moves the ensemble or the realizations. So it's the same thing as with this McKean-Vlasov, where everything happens simultaneously, that you don't just want to nudge the mean and the covariance matrix because these are secondary quantities. You really want to say, how do I have to rearrange my particles so that their statistics is coherent with, consistent with these two first moments. Of course, this doesn't require that the forecast is really Gaussian. You can also think of this as the best linear unbiased estimator, the blue estimator. And of course, it's also the case that these two conditions don't uniquely determine such transformation. And there are, of course, other games you can play. The Ensemble Kalman filter is doing this approximation. But you can also say, okay, I don't assume the prior to be Gaussian, and I do sort of the classic Bayesian update step, and then I just make the Gaussian approximation to the posterior. And that's different, right? So first, in the ensemble Kalman filter, at the beginning you make a Gaussian approximation, then you do Bayes' theorem, and that gives you a Gaussian approximation. You can also say, okay, I do first Bayes, and at the end I make a Gaussian approximation, and I also get, but it's not going to be the same mean in the covariance matrix. That's a filter that also has been proposed, but it's not quite as robust in general, it seems. But it's another possibility. So just saying that there are many ways at what point you make an assumption about your distributions you're working with. Right? You could also do this variational Bayesian stuff. Of course, it would probably be a bit too costly. And say, well, I do again the Bayesian step, as we discussed this morning, and then you make a Gaussian approximation using variational Bayes. And then rearranging particles so that they sit at the right position so that it looks, I mean, the first two moments, the mean and the covariance match. Anyway, so now here as an example, I show you the update for the stochastic ENKF. That's the one that Evanson and well, later it was corrected, but that's sort of the first incarnation of the ensemble Kalman filter. So you have these estimated quantities, and then the innovation, as I said, is that you add to the to what your model says the observation should be. You make it look like an observation, right? The observation model would exactly do this, right? You have measurement errors. So you artificially add this, and then you compare it with what you actually observe. And that turns out to be the right thing. So if you now take expectations across all this stuff, and you take the limit of particle number go to infinity, you can show that you're really reproducing the proper first moments, first two moments. So it's correct. In the original paper of Evanson, actually, that wasn't there. So he applied the standard Kalman update as you would apply it to the mean to all the particles, and that leads to an underestimation of the covariance matrix. So that is not right. And people quickly found out of it because the spread got too small of the ensemble, and if the spread gets too small, that eventually leads to filter collapse because basically you're getting overconfident about what you know about the errors, and then you don't trust the observations anymore. And if you don't trust the observations anymore, then of course the system goes off and goes haywire. Okay, there are many other variants of the ENKF. And so what is the common structure of all these filters? And it's very simple. And you can see it on this slide here. So all these filters have one thing in common, that the new ensemble is a linear combination of the old ensemble. Period. And the way you do the linear combination, that's how they differ. And that's the playground. And so let's go through this in the stochastic formulation. Basically, what you do, you split apart the approximation of the covariance matrix, which goes into the Kalman gain. So the Kalman gain is the covariance matrix, and then this inverse matrix, and then multiplied by the innovation, essentially, right? So that's the thing that does the transformation. Now you rip apart the estimate for the covariance matrix, and there's also a little trick that if you think of the covariance estimate, then it's the ensemble member minus its mean, ensemble member minus its mean transpose. And they sum it up over all. Now, in the first of these two products, you can actually take the mean out because that's a zero. It sums up to zero. So you can actually take ensemble member and then product ensemble member minus mean transpose, sum it up, and that's an estimate. This is equivalent estimate to the covariance matrix. So that's the mean is sort of redundant. Of course, mathematically, it looks nicer to have the mean in there that's nicely symmetric, but it's not necessarily. It gives you the same result. So that's how I got this here. So this is the mean I pulled out. And this is the rest. So the index here, I, is the same. And this is the estimate of the covariance matrix. And then here, the rest of the whole thing then depends on the index J. So that's the update for the Jth analysis, or the Jth particle. And so this is just, this whole thing collapses down to a scalar for each given index I and J. And of course, it depends on the whole ensemble, but it's just a scalar in the end. So that's this.